observability stream. In that stream, we work on making sure that everything that happens within the platform is observable. So at the high level, that means we build things like monitoring tools, alerting pipelines, infrastructure for dashboards, for which you use Grafana quite a lot. And in this talk, I'm going to be talking about performance killers for Elasticsearch. I'm going to be throwing you back to a series of incidents we had for Elasticsearch. And we're talking about what led to those incidents and our journey investigating it. So I also want to emphasize that this is performance killers. We're not going to be talking about performance tuning or trying to get the most out of our hardware, but really about all the little gotchas and sharp corners that we ran into and the configuration mistakes that we wish we could have avoided. So without further ado, let's get right into it. Yes. Where's my mouse? All right. I think that should. It doesn't go away, I see. Let me put it somewhere unobtrusive. Floating controls, where's that? More? Hide floating controls, hide video panel. Hide floating. I've actually always wondered how to do that. Yeah. Learning objectives already met. All right. Picking up where we left off, talking a bit about how we use Elasticsearch at Adyen. This is an example of one of the dashboards that Elasticsearch is powering. It's used across the company for both enabling support teams, but also duty teams, on-call engineers, but also regular engineers to understand how their products are being used, which means that when we do have an outage, the impact can be quite large. And we want to, of course, minimize the amount of outages that we have, because when they do happen, our ability to investigate issues is severely diminished. So I said I was going to cast you back to what things were like. This was the state of things about a year and a bit ago, so December 2021. We would see things just seemingly would go bad. We were seeing extremely long garbage collection pauses. CPU would spike into the stratosphere. Ingestion would go straight to zero, seemingly whenever it wanted to. Looking at nodes in the cluster, half of them would just disappear, and then all of them would be gone. Yeah, and CPU is high. And of course, the obligatory incident tickets, timeout, doesn't work, please fix. And we had absolutely no idea what was going on. We were trying to think, okay, what could cause CPU spikes? What is going on? But we didn't have enough to come to an answer, which meant that the solution was simple. Given no other information, the only thing we could do is restart everything. So we call up our infrastructure engineers and say, just turn it off and on again, please. They would log into every node, try and stop it, and then move on to the next one once it's restarted. However, even in this case, the clusters would not respond to a stop. They would not respond to a sigint. We just had to send them sigkill and hope for the best. So we did have that backups of the data. So if things were corrupted, we could recover. But this was not a great situation. Not only was it, well, it was solving it with beating it with a hammer, but also it was a manual process, and it took a lot of time and it took a lot of resources from our infrastructure teams. And that time is valuable, and we don't want to waste it. So we wanted to get to the bottom of this, which meant that the first thing we had to do is collect more information. If we can't solve it, we need to at least see what else is out there. And we had a few hypotheses, the natural hypotheses. Maybe some user is killing us with a crazy query. At the beginning, we weren't so sure about this hypothesis because we thought, well, Elasticsearch has a lot of nice circuit breakers. It has a lot of tools to stop users from doing stupid things. But we also know that you should never underestimate users. So to do this, there's a nice feature called slow logs, which we could then enable to get more information about the queries that the users are running. Everything above a certain time threshold would be logged. We had a little bit of a struggle to convince that this is a good idea because these logs would be stored in another Elasticsearch cluster, and this cluster was stable. So when we say, oh, we want to add more load to a stable cluster, there's a little bit of uncertainty. Oh, we don't want to make all clusters unstable. But once this was cleared, we got the slow logs, and it was nice. Another hypothesis, maybe our hardware configuration is doing something strange. Possibly we have 29 master nodes and 1 data node. We don't know. It should be checked. Maybe the network connection between the nodes is really bad. We need access to the exact configuration in hardware and the configuration of each node, just to investigate. And then finally, our last thought, maybe we're just using Elasticsearch wrong. Maybe we don't know what we're doing. So we decided, let's just read through GitHub, see if there's some feature we're missing. Maybe there's even a bug that we've stumbled across. Oh, now, okay, reading the full code on GitHub is going to take a long time, but we find that there's a lot of valuable information in things like GitHub issues, merge request discussions. So we thought it's a valuable source of information. Let's dig into it. And this will be obvious in retrospect. The second two weren't so useful, and slow logs were incredibly useful. Immediately as we enabled slow logs, wait for the next incident, we get some nice information. CPU spikes and outages correlate with complicated queries. Now, this is such an obvious statement. I'm sure you could have guessed it from before this presentation even started. The word complicated here is doing a lot of heavy lifting. What I mean by complicated, or what we saw in the case of complicated queries, is they had a lot of fields that they wanted to aggregate over. So we'd see something like, give me the count of queries per host, per user, per request ID, per error message, per anything you can name it. So to understand what our hypothesis was, we needed to understand how aggregations work when running a query in Elasticsearch. And Elastic themselves, they provide this nice diagram. I've stolen it from your blogs. You see here, we have a nice user. He wants to know something. He sends a request, an aggregation with 1 million fields to aggregate over. It hits a node. This node becomes the coordinating node. And that coordinating node then sends out other requests to the relevant data nodes. Those data nodes then figure out what data it needs, what data is needed, and sends it back. And the coordinating node has the responsibility for constructing the final response and sending it back to the user. And everything there sounds totally fine. However, let's think about how large a potential response would be if we specify 10 trillion fields in an aggregation. What we know is that there's going to be 1 bucket per unique value of all the fields, and therefore, the size of this response is going to be the product of the cardinality of every field we aggregate over. So if you're thinking request ID, host, data center, client ID, the cardinality of each of these could be a couple thousand, maybe up to 1 million. Multiply them all together, and you're easily looking at about 1 trillion possible buckets. Long story short, this coordinating node is going to struggle to produce that response. Now, once we had this hypothesis in mind, a little bit of astute Googling gives us a nice solution for this. Search max buckets. So this is a parameter that if an aggregation is starting to build more buckets than this, just abort the query. It would have been great if this was already set, but in our current version of Elasticsearch, the version we were using at the time, the default for this is unlimited. Allow as many as the user requests. In more recent versions of Elasticsearch, a more sensible limit is set, but we were not running such a version. So with this hypothesis in mind, late one Monday, all the necessary people gathered, and we said, all right, let's just set it to something finite and hope for the best. I mean, we had a reasonable belief that this was the solution, but it's, of course, a breaking change. So downstream could break, and if it breaks, we might need to roll back quickly. But as we applied the change, to our surprise, there were actually very few breakages downstream. And our hypothesis for why is that most of our critical users are human beings. And human beings typically don't deal well with trillions of data points. So most of the realistic use cases only need a couple thousand data points. And in the case where there are trillions of data points, it's usually human error. And in that case, it's more useful to give an error message than to kill the cluster. There were some breaking changes, but typically they would be only a little bit above the limit. So a little bit of tuning brings them below the limit. And we did have some non-human users, mostly alerting systems. And in those cases, we have more control over exactly how they're querying. And there is this nice feature, composite aggregations, that lets us take one big query and make it many small queries. And the cluster was happy about that too. And with all of this work done, we were ready to see the amazing impact that it had on our cluster. We still had outages. So it wasn't great. Now, I don't want to make it seem too negative. We did see a little bit of improvement here and there, but our work was not done because, well, our users were still complaining. So we had to go back to what we know. Reconsidering the facts, our slow logs were still helping us a lot. We can see that the outages, they still correlate with specific queries, but these queries aren't the same complicated ones that we saw before. They would still aggregate over something, but this time it would only be about one field. And maybe it'll have a long time range, but we didn't think that was so strange. And even if the aggregation was large, we thought, well, search max buckets will be protecting us from large aggregations, even if it's one field or many fields. So we kind of put this away for now. But looking closer at the slow logs, there was another strange aspect. We have a 30-second timeout configured on the cluster, but these slow logs were taking of the order of minutes. We could see it, which was also strange. And if we tried to cancel these queries as they're running, they don't cancel. And if we try to restart the nodes are not responding to SIGINT and they need to be killed violently. And at this point, the value of digging through the GitHub issues and merge request discussions starts to show itself. There was one feature that came to my mind as I was looking at all these pieces of information. And I'll spend a little bit of time discussing it, and then you'll see maybe why it came to my mind. There is this nice feature called global ordinals, a convenient data structure for speeding up aggregations. A little bit about why this exists. It's quite nice, actually, despite hurting us later down the line. In Elasticsearch, obviously, the raw JSON isn't stored as text. It is stored in a more natural representation. It's compressed, which means that each document isn't storing, say it's a log line with a severity level, error, info, warn. That text is not going to be in the document. It's going to be in some other dictionary, and the document itself will just have a number that refers to it, or some other reference. Which means that if you're doing an aggregation, you can't refer to this number because this number is an implementation detail of the segment that the data is stored in. And different segments could have different numbers. So if you want to do an aggregation, you either have to fetch the text itself, or you can build a nice data structure, global ordinals, which will be unique across the entire index, I believe. And then when you do the aggregation, you look at the ordinal, you look it up in global ordinals, and then that's the reference you use in your bucket. One detail that strikes us is that since Elasticsearch doesn't know which fields it'll use for aggregations, this data structure is built lazily when needed, so at query time. And how this became an issue is that obviously as more data is being written, as new segment files are written, this data structure needs to be reconstructed because now the data is different. Which means that every refresh, we have to throw this away and rebuild it. And our refresh is 30 seconds, which means that if it takes more than 30 seconds to construct this data center, we've wasted a whole bunch of time. And our slow logs were showing that it was taking minutes to do something. And furthermore, as we noticed in the issues discussions, timeouts and cancellations are checked when a query is reading data. So there are certain checkpoints at which timeout will be checked, and all of those are in the reading data stage. So if your query is always in the creating global ordinal stage, it'll never check if it needs to timeout or cancel. So here we're starting to explain why our queries weren't timing out, why our queries weren't canceling. But let's also think about why we were seeing issues in the first place. Because global ordinals is a nice data structure, what is the problem? Looking again at our slow logs, we notice the issue. The aggregation is over an ID. So imagine you have something like trace ID and a user, for whatever reason, let's not blame them. They want to see the count of all events per unique ID, per UUID. This is always one for all UUIDs, but let's not blame the user. They want to see what they want to see for whatever reason. This aggregation causes Elasticsearch to decide to construct a global ordinals map, which will contain at least one entry for every unique value of the field. So imagine you have a UUID. Over the entire course of your data, you may have a couple billion unique values for that UUID, which means that this table is going to have about 1 billion rows, or the data structure is going to have about 1 billion rows. At best, they are numbers, so that it's a few bytes per row, which means we're looking at a few billion bytes, which is a couple of gigabytes. Now, that's about what a node has, is a couple of gigabytes. So it's not great if a node needs to allocate that much data to global ordinals, on top of the fact that it takes a lot of time. So what happens is the node is constructing a massive global ordinals data structure. We're seeing huge GC pauses because it's running out of memory. It wasn't unusual at the time to see garbage collection pauses lasting in the double-digit seconds. So master nodes are then checking like, hey, is this node still alive? It's garbage collecting. It doesn't respond after a while, and the master node, oh, well, it's clearly dead. So let's redistribute all the data. You know, we're a distributed system. We need to be resilient to faults. Redistribute all the shards. And now we go from a state where we have a few nodes that are dead. Now all of our nodes are struggling because they're dealing with all these new shards coming in. So all our nodes are struggling and all our users are unhappy. So what are we going to do? There are actually strategies to tell Elasticsearch, stop, don't produce global ordinals. I know what I'm doing. But that's complicated. So instead, we just said, let's not allow any aggregations on ID-like fields, because why would you ever want that? It took some convincing to tell users, you don't want this. Like, it's going to be one every time. You don't need it. But eventually, we did convince them, and they were happy. And after we disabled aggregations, we were actually quite impressed to see the effect. We have this graph here. There's a lot going on, but the only thing you need to know is that this green line is the average query time in milliseconds. So you see before, average, it's often above 1 second. Right after we make the change, nice and flat. Oh, okay, there's still like some spikes, but you know, massive improvement from the past. And going on from this time, our sporadic catastrophic failures had massively reduced. And we were happy about it. We said, job good, well done. But what did we learn? The first point is the most natural. Whenever you are lost and you don't know what to do, just see what possible information is there that I don't have and try and get that information. For us, the key source was slow logs, but a lot of the insights also came from GitHub issues and reading through discussions on the project itself on GitHub. That was really an invaluable source. 2, have lots of spare ingestion capacity. We were happy to tell our users, oh, we only had an hour incident. What are you complaining about? But to them, they don't say that the incident's over until all the data is caught up. So in our case, we had about 50% spare capacity, which meant that when we were catching up, the ingestion could be about double of the normal rate, sometimes triple. But that means if we have an hour incident, it takes us maybe 2 hours until we're caught up to the real time, and our users are happy. But if we are running the cluster closer to its limits, this multiplier becomes tragic. Like imagine you only had 10% extra ingestion capacity, then a 1 hour incident, the math isn't going to work out, but it'd be like, yeah, it'd be long. It'd be like 10 hours until you're caught up. Don't double check that. But something like that. So it really showed that you have to have a little bit of slack. And three, we felt it usually gets worse before it gets better. I think we were seeing that these queries were taking a couple of minutes, but the incident or the outage lasted way longer than a few minutes. And this was because the cluster needed to rebalance its shards. It needed to distribute the data so that it's still fault tolerant. And of course, it is a distributed system. It needs to be fault tolerant. And there wasn't really a way to get around this. If the nodes were truly dead, Elastic couldn't say, yeah, whatever, I don't care. So this is just a fact that we have to accept. And finally, yeah, okay, we have to stay updated. We got burned because we weren't on the most recent version. Search max buckets is set to a nice, sensible value on the recent versions, and we weren't on it. So that's another argument to stay up to date. So I hope you learned something from our pain and struggles. Thank you. Do we have time for questions? Yeah, are there any questions? All right, yeah. So I compressed things a lot, and I showed multiple incidents at the same time in some slides. I would say that we started paying a lot of attention to this around the start of the new year, 2022, and the final resolution of like, oh yeah, global ordinals, that's it. It was around, I think, April. So we're looking at a few months here. Yeah, sure. Yeah, so it's about 30 nodes. I think average ingestion rate is sitting around 50,000, 80,000. It varies a bit. Um, I believe distribution is about maybe 20 something data nodes and a handful of 5 master nodes. So actually, I didn't send out any new forum posts. I was digging mostly through old forum posts. Um, there was a common theme in a lot of forum posts, which would be if you're running a version less recent than 7, the answer is going to be update. Come on, what are you doing? Um, but also, we already got a lot of information from GitHub, just digging through issues. So that was thankfully enough for us. I think if it was taking even more time, then we would get desperate and start posting wherever we could find. But yeah, in the end, I didn't reach out to anyone, just reading rather than posting.